When Zig outshines Rust, memory efficient enum arrays. Okay. Enums are tagged unions whose variants vary in size, are prone to significant memory fragmentation in Rust. Okay, type 1 in the chat, by the way. Who knows what an enum tagged union is? Okay, these are not TypeScript enums. Okay, so if you know what a TypeScript enum is, don't think they're the same. All right, sorry, I asked this question incorrectly. 69 in the chat if you have just absolutely no idea what they are. Okay, there's a lot of people. So let's hear. I'll give you a quickie. Can I give you guys a quickie? So that way we make sure everybody's on the same page. It's pretty straightforward, okay? So here. I don't think I have a cargo here. I'll just cargo and knit a new project in here. Whatever, that's fine. We'll go to main. All right, so an enum here, we can go like this. Enum foo, right? So I've created an enum in Rust, and now I can say some different types, right? I can have a bar, which let's just say it has a subtype string. I can have a baz here, struct other, right? And let's just say that it has a, which is an I32, and a b, right? I can have a baz that contains an other. I can also have a nothing element, right? And I can put that at the tippity top, little optimization, whatever, not a big deal. But this is an enum. What it does is it actually shows it's a way to tag different types, right? So what happens underneath the hood is that it has, I think it's just your system word size of what type it is, and then the rest of the memory is devoted to the type underneath the hood. So that way, the equivalent of this in TypeScript would be something like this, right? Type foo equals undefined or string or other, right? Like, I think that would be the equivalent, but they're not quite the equivalent, right? They're not quite the equivalent, because when I want to go like this, foo equals foo bar hello into, there we go. I've just created a bar, right? But it's just a foo size, right? So it's a just type foo. I can pass this foo to any function, and it's just a foo, and it takes in function foo. It takes in that type foo. To be able to do something here with foo, I have to lift it, right? And so I have to lift the actual inner value out of it. This one would be, if it's a type bar, if it's a foo bar, then we get the string out. If it's a foo baz, we get the other object out. So it's a little different than TypeScript, because TypeScript, what you do with TypeScript is that you'd go, if undefined, handle the undefined case. If A is in the thing, if type of is string, do the thing, else it's the other one, right? So it's kind of like you have to do a bunch of if-elses as opposed to a pattern match on top of it. Plus, it's efficiently stored. Its type is stored as part of the information. So this pattern match is effectively the same thing like comparing a integer, right? So it's very fast. It's just a comparison of an integer, whereas a switch is not a comparison of an integer. Let's see, you can serialize a tagged union. With TypeScript, you cannot without keeping the type. Exactly. So this is another cool part about a tagged union. You can serialize them, like into JSON, and then deserialize them back into that tagged union structure. It's pretty cool. Why did I use into? Okay, well, this is just a Rust question now. This right here is a stir. Why is it a stir? When you compile a program and you just raw dog a string right into a program, this is actually the type, the underlying type is a static, oh, I don't know how I got that little T in there, is a static stir, because it's in memory somewhere, right? That string is like actually in the memory of the program. If you looked at the binary, there would just be a hello somewhere within there. And so it's just a reference to that point. So to create it into a capital S string, which is like an object, right? Which is its own object with its own underlying copy of memory, which that memory hello is located somewhere on the heap. That's what I just did. But Mr. HCMX made an improved morph DOM. Oh, cool. That's something I would want to look at. Okay, anyways, so now that everyone knows what a tagged union is and kind of how to use it and what was going on there, let's go back into the article. So consider this one, foo, there you go. So here again, here's the tagged union with its different types. A is a U8, B would be a type U16, 32, so here you go. Because of the space needed for tagging and alignment, this type is 16 bytes long. This makes sense, because remember, so one thing I forgot to say is any tagged union contains, the size of a tagged union contains the tag, plus it contains the largest submember. So this member's 1 byte, this is 2 bytes, this is 4 bytes, this is 8 bytes. So one tag, which is usually system width, so that would be, a U64 effectively, then another one of these, so that'd be 16 bytes, which they say right here, right? You can see that right here. It contains each one of the units. And that's just how a union works in C. It's how it works in any language. And you can't complain about it in TypeScript because, well, you're using JavaScript, which everything is like a minimum of 16 bytes. It's just gigantic. This presents real pain when collecting a large number of them into a vec or hash map. Okay, this makes sense. This actually makes sense. So this tag and padding thing is kind of interesting. You can have a lot of them, obviously. The reason why they choose this, I believe, is reading speed, right? It's just more efficient to read out an entire word than it is to read out some U8. And so just a thing to think about. You can hand roll specialized data structures for particular enums that reduce fragmentation to a minimum, but doing this generically for an arbitrary enum with maximum memory efficiency is close to impossible in Rust. The only option we have are proc macros, which compose poorly, no derive on third-party code or type aliases, and are not type-aware unless using workarounds based on generic const expressions, which infect the call graph with the verbose trait bounds and don't work with generic type parameters. So all of this to say, I have no idea what he's talking about, but that sounds terrible. Or congratulations, I'm sorry. Zig, on the other hand, lets us perform the wildest data structure transformations in a generic, concise way. Well, that's exciting. I like that. I like the sounds of that. Because I understand the problem, right? So just for everyone to understand the problem, let's say you had a million foos, right? And almost every single foo is an A. And you have very few of these other ones, right? Like, let's just say foo represents a UTF-8 encoding, and it's an English paper. Most of them are going to be this. Maybe there's some sort of weirdness that actually causes some other large character, right? I know U64 is not UTF-8 encoding. I get what you're saying. And so what's going to be is that you're going to have like all this unused space in every single spot, right? You're only using 2 bytes out of 16, 1 out of 8. So you're only using like 12.5% of your memory at any one time, almost throughout the entire array, which ends up being 16 megabytes, which is a lot of memory. So I get the argument. The argument sucks. You want a tight structure. You want to pack it. You want to pack it tight. But that's the problem about unions. They need the space. They have to have the space because you have to be able to lay out memory in a certain way. Let's see, before I go to the implementation details, I'd like to explain why reducing the aforementioned memory fragmentation is useful in practice. Okay, background. To me, one of the biggest motivators for efficient enum arrays have been compilers. One problem that keeps coming up when designing an AST is figuring out how to reduce its memory footprint. Big ASTs, girl, I like big ASTs, can incur a hefty performance penalty during compilation because memory bandwidth and latency are frequently bottleneck in a computer front ends. Chandler Currat's video on Carbon Compiler has been making the rounds on language forums. In it, he describes how he parsed Clang AST regularly consumes 50x more memory than the original source code. Dang, that's a lot of... I mean, think about it. Source code is largely like white space, too. There's so much white space in code. And you're telling me that it's like 50x more memory? That's crazy. All right, so what does this have to do with enums? Well, the most common way of representing a syntax tree nodes is via some kind of recursion or recursion-like data structure. Let's define a node for expressions in Rust using our new type indices for indirection. Expression unit, number, binary. So there you go. So, like, this looks just like this. If you've done anything with like the Thorsten Ball book, building an interpreter, this looks like you immediately recognize this, right? We can write an AST node in OCaml. Ooh, let's go OCaml. Let's go OCaml. There you go. You got the exact same thing. This all looks good. A big difference compared to Rust is that we can express truly recursive data types without any form of explicit indirection. That's because the runtime system and garbage collector take care of memory bookkeeping for us. Yes, this is true. It just makes everything in OCaml is just slightly easier. You just have to learn a new syntax, which is emotional, which is what I want to do, but I just haven't done it yet. The problem we have now is that we want to improve packing efficiency of those enums. A simple vec expression will consume size of enum. This is actually a really great article. I love where this is going. This is fantastic. Amount of memory for every element, which corresponds to the size of the largest variant plus tag plus padding. Luckily, there are some ways of dealing with this. Reducing fragmentation. Let's take a simple example of a 3-variant enum with member sizes 8, 16, and 32 bytes. Storing those in a regular vec would look something like this. This makes perfect sense, right? Is everybody on board with this? By the way, this guy is using Excalidraw. Can we all take a second and appreciate a little bit of Excalidraw? Right? This is some good Excalidraw skills right here. I think he's using Excalidraw. Dude, OCaml is rising. OCaml is a big W. I'm getting excited about it. The most common way to improve packing efficiency is by keeping the enum variants as small as possible using tagged indices. For example, in Rust, take a look at the tagged index crate used by the compiler, or check out the recent blog post on small string optimizations. You'll find these optimizations all the time in high-performance code, like language runtimes, garbage collectors, compilers, game engines, and OS kernels. Okay, very cool. We won't look at those, but exciting. Unfortunately, that doesn't completely solve the fragmentation issue. The other way to tackle the container... the other way to tackle the container type directly. Oh, whoopsies. The other way is to tackle the container type directly. We could use a struct of arrays approach to store the discriminants and values in 2 separate allocations. In fact, that's what the self-hosted Zig compiler actually does. Okay, this makes sense. An array of structs approach, practically ECS at this point. The tag and union are stored in 2 separate allocations, so we're not paying for padding anymore. However, the union collection still has the variant fragmentation. Yes, this makes sense, because you have to store... Does this make sense? Is everyone understanding this? Like, if you still have an array of 8s, 16s, and 32s, that still means you have to have an array of only 32s, and all these 8s and 16s just fit in the 32s, right? That makes sense. Because of Zig's stage compilation, we have a container types that perform this SOA, struct of arrays, transformation generically for any type. In Rust, we're constrained to proc macros like structs of arrays derived, which has several downsides. We can't place derive on third party. Yep, we've already talked about that. Reducing variant fragmentation. This structure of array transformation reduces a lot of wasted padding introduced by the enum tag, but still isn't optimal. To really get rid of fragmentation in the values, we can create 1 vector per variant. Okay, this would be hard because now you have to use, because one thing they're missing in here is that you'd have to have some level of bookkeeping, right? You'd have to have something that tells something else where to look for this information, right? You can't just do 3 separate arrays for freezy. Size equivalent classes. We could stop here, but let's consider enums that have lots of variants that can be grouped into small number of clusters with the same type size. Okay. A, B, and C, and D, these are all the same thing. Okay, nice. Yep. E, F, yeah. And then I, 4. Okay, beautiful. Look at that. A U32 and a U32. Wait, hold on. Wait. These aren't the same. I looks larger. Oh, I is supposed to be thinner. It's hard for me to read what I is supposed to mean. Anyways, okay. As you can see, the once per variant approach would add 15 vectors. It's like the number of reallocations in the system's call would increase substantially, and that requires a lot of memory to amortize compared to the native vec. Yeah, or the naive vec. The vector, it's also just super hard. Like, this would be such a hard thing to program. Can we all agree that this is like virtually the impossible? This solution feels impossible to program. The vectors may also be arbitrarily spread in memory, leading to a higher chance of cache conflicts. The AOVA collection, I actually don't know what that is. Collection itself also consumes a lot of memory, bloating any struct it's embedded in. Now, if we group every variant by size, we get 3 clusters, 2, 4, and 8 bytes. Such clusters can be allocated together into the same vector, therefore reducing the number of total vectors. Okay. So we have a bunch of different kind of vecs, right? This makes sense. You collapse them all based on their size. You could say this dense version of our AOVA pattern. However, once we co-locate different variants of the same allocation, we lose the ability to iterate through the vector in a type-safe way. Exactly. So what he means by that is you literally just can't match the type. You can't just for match. You have to... I'm not even sure how you'd walk through this in order to begin with. How do you know what order is what order? And when it comes to an AST, ordering it's pretty important. So I don't quite see how we do something with this yet. If you lose access, if your access pattern does not require blind iteration, which can be the case for flattened index-based tree structures, absolutely. This might be a worthwhile trade-off. Okay. I've implemented a prototype of this data structure in Zig. The most important pieces are the compiler built-ins that allow reflection of field types, byte and bit sizes, as well as inspecting discriminant. Okay. So at its core, this performs a straightforward compile time reflection to compute the clusters and field to cluster mappings. We do a pseudo-dynamic allocation using a stack allocated vector. This cluster information is used to construct the AOVA data structure. Okay, very cool. You got to, this is kind of wild. This would take a while to digest, so we're just going to have to jump forward. If you want to do type-safe iteration, you could pay the cost of padding and add the tag back in. Okay. Okay, very cool. I don't understand why the tag is matching these sizes, right? That I don't quite get why the tags are matching sizes. If padding is too much, you can do a structive arrays transformation on each array variance. Yep, you can do that. That's cool. That's cool. As you can see, there's quite a few trade-offs you can make in this space, and they've all depend on the concrete memory layout of our enum. Wow, this is super complicated. Programming this correctly, it feels like an index nightmare. It feels like a genuine index nightmare to save all this, because there has to be one more missing array somewhere that is like this information of which one to access in what order. I feel like there's one missing piece in here that we're not seeing, and that's what I'm worried about, which is I feel like I'm kind of missing this. Let's see. Watching you, I get imposter syndrome. Don't worry about that. Maintaining the same memory boundary, maybe, so they can be stored inside of VEC as well, maybe. An array of pointers that are you can't do that in Rust, or it's very hard to do what you're saying in Rust. You know what I mean? Git work tree. There's just nothing that needs to be changed, I don't think. Anyways, let's keep on going. All right, so as you can see, there's quite a few trade-offs that we can make in this space, and they all depend on concrete memory layout for this enum. While creating such a data structure is pretty straightforward in Zig, creating any of these examples in Rust using proc macros is basically impossible. Completely agree. The moment you enter into proc macro land, you've pretty much entered into the impossible land. Sorry, I'm trying to move something below. I think I just bonked my camera. My bad. The reasons being that proc macros don't have access to type information like size or alignment, which could have, let's see, while you could have a proc macro generate a const function that computes the clusters for particular enums, this function cannot be used to specify the length of an array for a generic type. Another limit to Rust generics is that the implementation of generic containers cannot be conditioned, or whether the given type is an enum or a struct. In Zig, we can effectively do something like this. That's pretty cool. That's pretty cool. Again, I think Zig has a bright future. I think Zig really does have a bright future. It has, and the thing is, it prevents you. It has nil pointer safety, which I think is like 80% of all the issues is nil pointer safety. And so you have nil pointer safety, and then it has a bunch of other safety. It has tagged unions. It has errors at values. It has syntax to handle errors, so you don't get the if error equals nil go problem. It's nice. It's a very nice language. I do want to see, the problem is I'm stuck between what's my next big language learn, because I finished my, I'm done with the Rust learning. I don't really necessarily need more Rust learning. I'm not going to benefit a ton by learning the deeper parts of Rust. And so my next one is either Zig or OCaml. And I just don't know which one to do. I know people love Elixir. They always want me to learn Elixir. I just am not sure about it. I've only dabbled in Zig. I've dabbled in Zig and just kind of checked it out. It has null pointer safety, but you can still leak and use after free, etc. Sure beats C, though. Yeah, it sure does beat C. It sure does. Why not both? Because it's time consuming. It takes a lot of time to learn a new language, and so I don't want to learn something. I want to really get it done well. VS Chode. Hey, VS Chode. Thank you for the $50. You're in a YouTube video now. Thank you for that. Thank you for that. All right, let me finish this. Bonus, determining index bit width at compile time. While implementing my prototype, I noticed other ways of saving memory. For instance, if you know the maximum capacity of your data structure at compile time, you can pass that information to the type constructing function and let it determine the bit width of the returned tag index. With this tagged index when this tag index is included in the subsequent data structures, let's say another enum, this information carries over naturally, and the bits that we didn't need can be used for the discriminant. So Zig gives you the composable memory efficiency. Oh, that's pretty cool. I don't quite understand what this means, but I like the ending, which is that as you specify things downwards, everything can kind of compile to it and it just makes sense in Zig. And that's pretty cool to have composable memory efficiency. By being specific about the number of bits you need, different parts of the code can take advantage of that. And with implicit widening integer coercion, dealing with APIs of different bit widths stay ergonomic. Yes, dude, that's one thing Rust, I personally don't like this. I don't like that you constantly have to specify upward. Maybe there's some safety reason that I'm missing in Rust, but I don't like that a U32 can't be instantaneously promoted to a U64. Like, to me, that just feels natural. And it does make me a little bit wonky. And using like I size versus U size, it feels emotionally painful. Yeah, but I don't want to have to specify this, right? I don't want to have to think about this whole thing, right? Like, I get that you should never downcast. No, again, you're still making me think about it. Why not use usize then? Well, usize doesn't always work. Like a time API, time APIs either use U64 or they use U128, right? Like, if you call as milliseconds, you get a 128 back. So then you got this whole thing that goes on. Of course, but Rust already does a bunch of implicit stuff as it is. You know what I mean? So it's not straightforward. In a way, this reminds me a lot of refinement typing and ranged integers. So this ties a lot with my post on custom integer bit on custom bit width integers. By the way, Zig allows you to do custom bit width integers, which is crazy. You can do like a I-18. I don't even know what to do with that. Writing extremely efficient generic data structures in Rust is not always easy. In some cases, they incur lots of accidental complexity, and in some others, they're essentially impossible to implement. I think one of the biggest takeaways for me with regards to staged compilation was the ability to be composable on memory layout level. Yeah. Or to be composable on a memory layout level. If you're developing a system programming language that embraces efficiency and zero-cost abstraction, you should absolutely take another look at staged programming, and in particular, Zig's comp time. This is awesome. This is just great. Absolutely love that. Comp time is just the greatest. I think comp time is one of the greatest features of Zig. In fact, I'd argue that comp time is one of the coolest features of any programming language. I agree with that as well. And so that's the one thing I just love. Comp time. Comp time in Zig effectively allows you build these types. It's kind of like generics. You can kind of think of it like generics, except that you're writing code that executes at compile time. So you write Zig that creates Zig, but it doesn't feel like a proc macro or something that's really hard to do, right? It's not like Rust's proc macros. Virtually impossible. Proc macros, there's like 7 people in the world that can write proc macros. The rest of us are just too stupid / don't have 2 months of peer study on proc macros to write them good. I'm glad that this is your first comment. Orsgoth, I just want you to know you've made it into a YouTube video, and that you, my friend's very first comment is this, okay? Just want you to know that right now. Like and subscribe. Like and subscribe. Like and subscribe.